Hello. I just want to finish up the last two examples from 15.3 polar coordinates. So in this example, we're asked to change the iterated integral by converting to polar and then do not evaluate. I'm going to go ahead and evaluate because we want to also see how that's done, and in a video we have the time. So first I want to talk about the converting to polar because it might not be what you think it is. We need to convert, whoops, that's not what I wanted. We need to convert the bounds to polar by graphing first, and then we're going to convert the integrand in the differentials using, let's see, x squared plus y squared is equal to r squared, and dy dx is equal to r dr d theta. So that's the easy part, converting the integrand and the differentials. The more difficult part is converting the bounds to polar. And it's tempting to just replace the 2x minus x squared in that upper bound with just take all the x's and put in an r cosine theta. But I promise you that won't get you anywhere. So what we have to do instead is figure out, what is this shape that we're dealing with, okay? So I'm looking at this and I can see from the inner integral, we are dealing with y equals 0, which is the x-axis, and y is equal to the square root of 2x minus x squared. So the first one is just the x-axis. That gives me the lower bound. The second one, I'm still not clear on it, just because I wrote it out doesn't actually help. But if I was to square both sides, I might start to get a better picture of what I'm dealing with here. So I'm going to square both sides. And at the same time, I need to remember that my original function is just y equals the square root. So it's positive y values. All right, let's go ahead and square both sides. We get y squared is equal to 2x minus x squared. I should probably move everything to one side. When I do that, I get y squared plus x squared minus 2x is equal to 0. I'm starting to see circular things, but there's that extra minus 2x. And so it looks like I need to complete the square on the x squared minus 2x. So what happens is I have to think of well, let me just write it out. We've got y squared plus x squared minus 2x plus whatever number I need in order to complete the square. But if I add something to the left, then I better add it to the right as well. So that value there is going to be minus 2 over 2 all squared. Remember, that's b over 2 all squared that we're adding in. That just simplifies to be a 1. So I'm going to add 1 to both sides of the equation. Then on the left side, this becomes y squared plus x squared minus, well, let's see, x squared minus 2x plus 1 factors to be x minus 1 all squared, and this is equal to 1. So this is a circle with radius 1 and center at 1, 0. I can draw that. That's not a problem. So I'm going to draw it, and the center is a bit weird. That's okay. So my center is over here at 1, 0. I have a radius of 1, so I need to go out by 1 in 4 directions in order to get points on the circle's edge. Remember, the center is not actually part of the circle, but it helps us get where we need to go when drawing it. So now if I connect all these values on the edge of the circle, here is my circle. And I need to also draw in the fact that y equals 0 is part of my bounds. That's the x-axis. And since y was equal to the positive square root of 2x minus x squared, that means that I'm actually only concerned with the top half of this circle, okay? All right, so this is my region of integration. Now, everything is in the first quadrant. And since we're in the first quadrant, that means that we are dealing with theta values from 0 up to pi halves, okay? Now, when it comes to the actual, like my r values, those are going to be kind of weird. So I want to start with, like, I need to get the equation of this circle basically in terms of r. So let's see how we can do that. We have y squared is equal to 2x minus x squared, and I'm pulling that from up here when I would squared both sides. Because there's no square root, now I can go ahead and think about, all right, well, let's go ahead and replace some things. In particular, I'm seeing I could do y squared plus x squared is equal to 2x. The left-hand side, x squared plus y squared, is r squared. The right-hand side, I'll replace the x with r cosine of theta. Okay, subtract everything to one side. R squared minus 2r cosine of theta is equal to 0. Factor out an r. Leave behind an r minus 2 cosine of theta. That's equal to 0. And I get solutions of r is equal to 0 and r is equal to 2 cosine of theta. So that means my radial arm is as short as 0 and then it's as long as 2 cosine theta. So in other words, my radial arm is dependent on the angle, the theta that we're going through. And so it's going to change as theta changes. And that makes sense given that we're trying to map out this, so if we're on the x-axis, we've got a radial arm that has a length of 2. But if we go part way through, if we start sweeping out, right, we're getting stopped at a shorter and shorter length for our radial arm, and it is dependent on the value of theta. So this is how we get our bounds. All right, this means that 0 is the lower bound for r, and 2 cosine of theta is the upper bound for r. Okay, so that's quite a lot of stuff already just to do a conversion. My hope is that you can see that it's not actually clear how to do this unless you actually show some work. Like you gotta show yourself this stuff. Okay, now look at the x bounds. We didn't even talk about the x bounds. We just talked about y going from 0 to the square root of 2x minus x squared. The x bounds say x goes from 0 to 2. That's pretty obvious in my picture here. My x values there. I'm going from 0 to 2, while y went from 0 up to the top of the circle. I think I've got that all taken care of with the r and theta that I got. So let's go ahead and do the conversion and set this up. So my original integral, the integral from 0 to 2, and then from 0 to square root of 2x minus x squared of the square root of x squared plus y squared, dy dx is equal to, and it looks like I'm going to have for my theta values 0 to pi halves, for my r values 0 to 2 cosine of theta, and then I have the square root of r squared for my integrand, and my dy dx is r dr d theta. So that doesn't look too bad to integrate. Of course, the square root of r squared is just r. And so I have here the integral from 0 to pi halves, the integral from 0 to 2 cosine of theta. That is very messy. Cosine of theta. And then we have r squared in total for our integrand, and then dr d theta. Okay, we can go ahead and integrate. We still have the 0 to pi halves. We're focusing on the inner integrand, or the inner integral for our integrand. So integrating with respect to r gives me 1/3 r cubed from 0 up to 2 cosine of theta. And then after we evaluate that, we will go ahead and deal with d theta. All right, so if I plug in 2 cosine of theta, I still have my integral of 0 to pi halves. I have a 1/3 times 8 cosine cubed of theta, d theta. All right, so we need to know how to deal with cosine cubed. And it turns out there's a handy little trick that we learned back in Calc 2. It says if you have an odd power of cosine and like nothing else in your integrand, then you can split that up so that you have even powers of cosine and then a singular power of cosine. So what that means for us here is we have the integral from 0 to pi halves of 8/3 times cosine squared of theta times cosine of theta d theta. And the reason for doing that is that now we can rewrite the cosine the cosine squared as 1 minus sine squared, and we'll be able to then do a u substitution. So I rewrite again the integral from 0 to pi halves 8/3 times 1 minus sine squared of theta times cosine of theta d theta. This is a u sub. So if I let u equal sine of theta, then du will be cosine of theta, d theta. So it looks like cosine theta d theta, that's du, and then my sine is going to be, well, u squared there because I have sine squared. So playing with that a little bit, I'm going to use my indefinite integral and figure this out. I have a 1 minus u squared and then a du. Well, that's not too bad. I also have an 8/3, so I guess I'll go ahead and handle that. I get my 8/3 times u minus 1/3 u cubed, which becomes 8/3 u minus 8/9 u cubed. Okay, so I took care of the constant, I took care of all the functions, just replace the u with the sine, and we get 8/3 sine of theta minus 8/9 sine cubed of theta. We're going from 0 to pi halves. At pi halves, we have 8/3 times sine of pi halves minus 8/9 sine cubed of pi halves minus, and then here we get 8/3 sine of 0, minus 8/9 sine cubed of 0. Sine of 0 is 0, so those are going to go away. I'm getting no contribution when I evaluate at 0. However, over here, sine of pi halves is 1, and sine cubed of pi halves is 1. So in the end, I just have 8/3 minus 8/9, and I could write this as 24 minus 8 over 9 for a total of 16 over 9. I think that is right. Yep, that looks good. Okay, so we have a grand total of 16/9 for that problem. That was a lot of work. That was totally like a full page of work. So be sure to kind of, watch through this, carefully set your problem up, and then evaluate. All right, last one. In 4, we're asked to find the volume of the solid region bounded by the plane z equals 0 and by the paraboloid z equals 1 minus x squared minus y squared. Now, if this was a problem on an exam, you wouldn't know to use polar coordinates or not. So you have to think of polar coordinates as like a tool that you have, that you pull out of your pocket when it looks like it's going to be useful. So let's go ahead and set up in rectangular coordinates in the sense of I know what my integrand is, and then we'll draw a picture to see what to do about the bounds and see if like our domain of integration is what is going to tell us whether or not we use polar. Okay, so the domain of the region of integration shows us if polar makes sense. to use. It's not the integrand that makes us make that decision. If it was the integrand, then we would be in real trouble if we had a nice circular integrand and then our domain of integration was a triangle. Like, that's not going to help us. So we're looking for like circular things, arc-like things that would lend themselves well to using r's and thetas to come up with the region of integration. All right. So we're supposed to find the volume of the solid region bounded by the plane z equals 0. That looks like that's the floor of our height. And the paraboloid z equals 1 minus x squared minus y squared. This is the roof or the top. And it is an upside down paraboloid. And this is where, I've been warning all semester about how important it is to know what your shapes look like. We've been given the name and we've been given the equation. So they've given us 2 out of the 3 parts. What you have to come up with is the actual shape of that. So I'm going to go ahead and draw this. This paraboloid, let's see, go ahead and give myself an x, y, z octant. It is flipped over and shifted up 1. Okay. And then I'm going to go ahead and get 1s on my x and y axes because this is going through. Well, let's see, how would we decide that? So if we have z equals 1 minus x squared minus y squared equals z equals 0, then we have x squared plus y squared equals 1 on the xy plane. So I have a unit circle on the xy plane. All right, so I'm going to go ahead and draw that. Here's the top of my paraboloid. Kind of hard to draw, but that's about it. And my domain of integration, that's D. If we were to draw that, we just have a unit circle that we're dealing with. And so that's going to be pretty simple for us to come up with the bounds. So if this is big D, the domain of the region of integration, then that means we have a full circle, a unit circle. So R goes from 0 up to 1, while theta goes from 0 all the way to 2 pi. That gives us really nice bounds. All right, then so these are our bounds. For the integrand, we have the floor, we have the roof minus the floor, which is going to be 1 minus x squared minus y squared minus the floor, which was 0. So this is just 1 minus x squared minus y squared. Notice they have a minus sign in common. We'll pull that out, leave behind an x squared plus y squared. And remember, in polar coordinates, this means this is equal to 1 minus r squared. Okay, so if I want to set up a volume, I need my double integral, and those are going to be for r and theta. I'll have 0 to 2 pi on the outside. I'll have 0 to 1 on the inside integral. My integrand is always going to be the roof minus the floor, which we found to be 1 minus r squared. And then my differential, my dA, is r dr d theta. Okay, so now if we distribute that r, after that we can start to integrate. So after distribution, we have the integral from 0 to 2 pi, integral from 0 to 1 of r minus r cubed dr d theta. All right, let's integrate. With respect to r, this becomes the integral from 0 to 2 pi of 1/2 r squared minus 1/4 r to the 4th. And we're going to evaluate from 0 to 1. After we evaluate, then we'll be able to integrate with respect to theta. So it looks like I'll evaluate at 1, and then when I evaluate at 0, I'll get no contribution. So we get this integral from 0 to 2 pi of 1/2 minus 1/4, and then minus 0 d theta. A half minus a fourth is just a fourth. So I'm looking at the integral from 0 to 2 pi of 1/4 d theta, which gives me 1/4 theta, evaluated from 0 to 2 pi. So I get 2 pi over 4, which is equal to pi halves. That is the amount of volume that is underneath this paraboloid and above the xy plane when the domain of integration there is over a unit circle. Okay, so that concludes the examples for 15.3. Next time we'll take a look at 15.4, where we're dealing with applications. Please reach out if you have any questions.